Types of control valves and their application. Rotary valve preference and application guidance. In process applications permitting their use, rotary valves are generally favored over linear motion valves due to superior robustness, higher capacity, better turndown ratios, and reduced fugitive emissions. Valve selections, including pressure regulators, must align with the piping class and be free of cadmium plating or galvanizing on any component. In climates or processes where freezing can occur, all exposed mechanical parts, including solenoid valves and valve stems, require ice protection, subject to principal approval. Linear valves must be mounted with vertically oriented actuators. Installations shall ensure full clearance around the actuator and body to enable complete valve disassembly without pipe removal. Adequate space for hoisting equipment must be considered during valve location planning. Where shutoff Class 5 or VIs per IEC 600534-4 is mandatory, a dedicated tight shutoff valve, such as a high-performance butterfly or ball valve, must be installed in series with the throttling control valve. Metal-seated rotary valves may maintain Class 5 shutoff and throttling services, but should be used only where the control valve does not serve an IPF, instrumented protective function. Depressuring applications must not use valves in series. Control valve sizing and noise prediction considerations are detailed in the dedicated sizing appendix. Rotary valves, eccentric plug and segmented ball designs. Rotary valves featuring eccentric plugs or segmented balls represent the primary choice where applicable. These configurations offer economical and efficient flow control, particularly under moderate differential pressure conditions. Butterfly valves. Butterfly valves are appropriate in scenarios involving large valve sizes driven by high flow and low differential pressure, where eccentric plug or globe valves are unsuitable, or when chemical resistance requirements make lined butterfly designs more viable. Double or triple offset, high-performance butterfly valves are applicable in Class 5 or VEX tight shutoff services and can manage high pressure and temperature ranges. Butterfly valves intended for spring opening service must feature a removable valve body to enable extraction with the disc in the open position. If using wafer or lug types, supplementary hand wheels or spool pieces must be incorporated, both subject to principal approval. Ball valves. Ball valves are recommended for on-off service, especially in erosive applications where seat scraping is necessary. In throttling services, however, ball valves without specially engineered internals must not be used without principal approval. Their suitability under high differential pressure is limited unless modified with specialized trims like anti-cavitation or low-noise inserts. Linear motion valves, globe valves. When rotary valves are not feasible, two-way globe valves serve as the preferred linear motion alternative. For three-way configurations, separate sizing of each flow path is essential. Applications beyond instrument air dryers require explicit approval from the principal. Angle valves. These are ideal for services involving coke formation, erosion, e.g. slurry transport, flashing conditions, or solid-laden liquids. Angle valves are also used where outlet velocities must be minimized. Specialized choke valves for wellhead use fall under this category. Diaphragm valves. Diaphragm valves are restricted to on-off slurry service and require principal approval. They must conform to applicable valve specifications and are not suitable for precise throttling control. Plug valves. Used in niche applications such as slurry flow control, plug valves demand principal approval and must adhere to design specifications. Their application must be justified by process conditions that preclude other valve types. Gate valves. These valves should only be selected for remotely actuated on-off services where fail-safe operation is not required. Common applications include isolation of storage tanks, blender operations, pump suction shutoff, and wellhead control. Both gate-type control and on-off valves must comply with the relevant piping and design requirements. Rising stem ball valves optimized for dryer applications. These valves feature a linear actuator mechanism that first lifts and then rotates the ball using a helical guide. Pneumatic actuation is mandatory. Breakaway torque must be precisely calculated to ensure reliable operation at minimum supply pressures. These designs use non-contact frictionless mode to ensure long service life and are compliant with pressure isolation standards for both soft and metal seats. Self-acting regulators, pressure-reducing regulators. These are allowed only in clean service environments where operator intervention is not expected, such as gas blanketing or instrument supply pressure control. Internal self-relieving features are not permitted for blanketing applications. Back pressure regulators, to be used solely for maintaining constant back pressure in clean utility fluids or for auxiliary equipment lubrication and sealing systems. Their use requires principal approval. Differential pressure regulators, restricted to secured systems like instrument air or lubrication circuits of rotating equipment. All uses apart from instrument air supply must be pre-approved. Temperature regulators, self-acting temperature regulators are considered only for non-critical heating services where pneumatic or electrical utilities are unavailable. These too require principal approval. Solenoid-operated valves. Use of solenoid-operated valves is restricted to instrument airlines and specific hydraulic utility applications, such as loading arms, remote valve actuation, and wellhead control units. Their suitability must be evaluated based on system response and reliability requirements. Body construction and materials control valves. General construction requirements. In hydrocarbon service, control valves must feature either process flanged ends or welded connections. For non-hydrocarbon services, wafer or lug-type valves are only permitted upon principal approval. Split body valves are restricted and require specific justification and principal clearance. Bottom drain plugs are not allowed on control valve bodies. Valve bonnets must be bolted and use fully retained gaskets. Gasket selection shall comply with standard design specifications. Bonnet designs must enable full top access to internal trim assemblies for maintenance. Valve body sizing guidelines. Control valves in throttling service must not have bodies smaller than the required trim size. Oversizing the body up to the adjacent pipe diameter is acceptable in cases of future expansion or to limit outlet velocity. On-off valve sizing should consider operational pressure drops and process economy. Reduced bore ball valves may be selected to optimize cost. Preferred nominal sizes for control valve bodies are DN 25, 40, 50, 80, 100, 150, 200, 250, 300, and above. Valve sizes below DN 25 require explicit principal approval. End connection standards. Valve end connections must match the assigned piping class. Flanged ends shall comply with ASME B16.5 or B16.47, and the gasket contact face finish must meet ASME B16.5 requirements. Proper flange matching ensures uniformity in pressure containment and joint integrity. Dimensional requirements. Face-to-face dimensions for rotary valves, eccentric plug or segmented ball must adhere to ISO 5752, ASME B16.10, or IEC 605343 standards. Butterfly valve dimensions shall follow applicable valve specifications. Flanged globe valves DN 25 to 400, class 150 to 600 must also comply with dimensional standards listed above to ensure installation consistency and maintainability. Material selection for valve bodies. Valve body materials, including bonnet, bottom flange, fasteners, must align with project-specific piping class requirements. Where corrosion or erosion resistance is critical, internal lining is permissible upon principal approval. Full body internal lining is mandatory for seawater applications, such as deluge fire protection. Stuffing box and packing design. Packing systems must comply with fugitive emission and fire safety requirements. Only gaskets and packing materials approved for service conditions and listed in standard specifications shall be used. Use of asbestos or man-made mineral fiber packing is strictly prohibited. Grease or lubrication-dependent packing is also not allowed. For high differential pressure services or those prone to icing, e.g., compressor anti-surge valves, an extended bonnet must be provided to ensure thermal isolation of the packing. In cryogenic applications, extended bonnets are mandatory to position the stuffing box outside insulation boundaries. All stuffing boxes must feature externally adjustable gland flanges and gland followers. Where valves are shipped with loose glands, clear warning labels must be attached. The gland must be properly set before commissioning. Leakage prevention provisions. Leak control measures must align with the specified piping class. Bellows seal bonnets are to be considered for tight emission control, but must be paired with a secondary stuffing box and leak detection connection. For added safety, a vent port between the bellows and packing shall be included. Use above Class 300 pressure ratings requires principal approval. Alternatives to bellows seals include double packing arrangements with leak-off ports or spring-loaded packing systems. These must be designed to maintain integrity under all operational scenarios. Valve trim, control valves. Seat leakage and flow direction. Emergency shutoff valves must be configured for flow tending to close to ensure reliable closure under line pressure. For throttling control valves, especially those with unbalanced designs, the preferred configuration is flow tending to open to reduce instability and excessive forces near closed positions. Tight shutoff, TSO, may be required in one or both directions depending on process demands. This must be clearly indicated in engineering documentation. Balance type single-seated valves with pilot actuation are not suitable for TSO functions. Similarly, cage-guided or balanced trims are not allowed for services involving solids such as coke. Clean fluid service is mandatory for all balanced trim configurations, and their use requires prior approval. Trim construction requirements. Rotary and linear valve trims must feature easy, quick replaceable plug and seat ring assemblies. For welded end valves, all trims, including seats, must be removable from the top of the valve to support inline maintenance. Where trim construction is not integral, i.e., separate plug and stem, a locking mechanism is required to prevent disconnection and stem blowout. This locking feature must not breach the valve pressure boundary. Seats must be positively retained. Mechanical locking is required to resist vibration. Adhesives are prohibited. In environments prone to atmospheric fouling, linear valve stems may require protective covers. Valve shafts shall be designed to prevent blowout under any failure scenario, meeting standard safety design principles. Trim materials and surface hardening. Valve trim components, plug, seat ring, stem, must be inherently corrosion resistant. Where process fluids become corrosive upon air exposure, material compatibility with oxygenated environments must be confirmed. In erosive, cavitating, or high-pressure applications, trims must utilize hardened materials. Options include stellite or colmanoy surfacing or solid alloy components. These are mandatory for erosive and choked flow surfaces, cavitating conditions, within sizing limits, wet steam or wet gas with 5 bar pressure drops exceeding 20 bar at 300 degrees Celsius. Where service conditions allow, AISI 410 or AISI 440C stainless steel approx 550 BHN hardness may be selected for cost efficiency. All trims must be traceable via an assigned trim number as defined in applicable design standards, e.g. ISO, API 600-602 BS 5353. For extreme erosion environments such as choke valves, advanced materials like tungsten carbide or ceramics may be required. Any use of surface treatments or hard facings must be reviewed with the manufacturer to ensure suitability for specific process conditions. Special designs, control valves, trim fouling, and self-cleaning considerations. Special trim designs, commonly used for noise or cavitation control, typically incorporate small passages to reduce fluid pressure gradually. These narrow paths introduce fouling risk under abnormal operating conditions during commissioning or while flushing the system. Each application must be evaluated for fouling potential across all operating scenarios, including startup and emergency states. Where such trims are necessary, preference must be given to self-cleaning designs. These expand passageways as the valve opens, reducing blockage risk. Self-cleaning trims are mandatory for critical services such as anti-surge valves or IPF duties at safety integrity level 1 or higher, and are strongly recommended in all fouling-prone services. Pilot-assisted trim restrictions. Pilot-assisted trim designs, which allow smaller actuators by amplifying control forces internally, are not permitted without explicit principal approval due to their complexity and potential failure modes. Design alignment and additional requirements. All control valves with special trims must adhere to standard construction, safety, and packing guidelines. These include fire safety, gasket material compatibility, and valve integrity under process conditions. Low noise valves. Noise abatement must comply with applicable plant noise standards. If predicted sound levels exceed limits, Calculations must be validated by process engineering. Noise mitigation may include source treatments, special trims, diffusers, attenuators, path treatments, acoustic insulation, or increased pipe wall thickness, used sparingly due to cost. Selection must balance technical performance and economic viability in consultation with the valve supplier. Anti-cavitation valves. Where cavitation is unavoidable due to service conditions, anti-cavitation trims shall be used to prevent material erosion and hydraulic instability. These designs manage pressure drop across multiple stages, minimizing bubble collapse energy. Steam desuperheating valves. In high-pressure steam systems requiring simultaneous pressure and temperature reduction, specialized valves with integrated water injection may be deployed. These must be pre-approved and selection guided by both process and mechanical criteria. Choke valves for gas and liquid service. Gas choke valves, e.g. for wellheads, must tolerate maximum closed-in pressure, allow full range of flow control under varying well pressures, feature replaceable internals without removing the actuator or valve body, use stilted trims during early production, replaceable with tungsten carbide later. Liquid choke valves, e.g. for draining high-pressure separators, must withstand erosion from sand, grit, and scale. Use rotating disc throttling with eccentric openings. Incorporate upstream filtration and downstream pressure-reducing beans. Be modular with removable internals and tungsten carbide components. Meet Class V or V-Seth shutoff standards. Fire-safe design compliance. All valves intended for fire-exposed services must feature fire-safe bodies and, where applicable, fire-resistant actuators, accessories, and cabling. These systems must maintain integrity and operability under fire conditions, ensuring operational continuity and personnel safety.